This lecture will be on the beauty of kNN, which stands for k nearest neighbors. For this lecture, you're expected to have read chapters 2 and chapters 4 of An Introduction to Statistical Learning with Applications in R. Chapter 2 is Statistical Learning and Chapter 4 is Classification. These are the two sections of that book that goes over the k nearest neighbors approach. If you have not read those, pause, go read those chapters and come back. In this lecture, we'll go over two primary topics: kNN as a classification algorithm and kNN as a regression algorithm. And hopefully at the end you'll see how these are really just two variants of the same common approach. It's easiest to understand kNN, k nearest neighbors, as a classifier. That's primarily what it is. And first you have to go back to the fundamental problem of classification problems. Let's say that you have a data set with a particular response or outcome variable y and a set of predictor variables or input variables x, and you're trying to find the functional relationship between them. But unlike in the standard regression case in classifiers, y is categorical. In this case, let's consider y being binary. It's either 0 or 1 depending on the state of whatever y is coding. And x can be anything, but in this case, let's just consider x as being a continuous set of variables. So samples from normal-ish distributions. Now, the goal of classifier algorithms, as was gone over in the classifier lecture, is to determine the probability that y is in state k given a particular observation or set of observations in x. So what you're trying to do is determine a categorical state of y given the patterns you observe in x. Now, typically, if you approach this in, say, a logistic regression problem, what you're trying to do is understand x as being sampled from one of two distributions. In one case, you have samples in x that are pulled from a distribution when y is in a state of 1. Another set of your observations in x are from y is in a state of 0. So let's take a hypothetical experiment here as shown in this graph where, let's say, awareness of a nested image in a visually presented display increases as exposure time increases. And so you just take a collection of participants, give them one try at detecting the presence of a particular stimulus in a noisy display, and you vary the exposure time. So participants either see or are aware of the image or they're not. And the way to think about this problem is that you have a distribution of participants based on their exposure time that achieve awareness. That's the blue distribution when awareness is 1. And another distribution of participants who are unaware of the distribution based on their exposure time. Now, we've gone over methods, parametric methods, before that try to do this classification problem. K nearest neighbors is a non-parametric approach to this problem, and the logic is really simple. If you want to know what the state of any single observation of x is, it's more likely to be the same state as a near neighbor. Let's say xi here is more likely to be pulled from the same distribution as xj than it is from this observation xk. So the general interpretation here is that observations in x that are closer together likely belong to the same group or the same state of y. No other assumptions are required for k nearest neighbors. That's it. That's the fundamental logic of this approach. The smaller the distance between observations, the increased likelihood that they are pulled from the same distribution, that they come from the same state of y. That's it. You have no assumptions of distributional families. You have no assumptions of sampling. All it boils down to is that observations that are closer together are more likely to be of similar groups. And that's the basis of kNN classification, k nearest neighbors classification. Let's consider a two-dimensional scenario here. So I have two x variables, x1 and x2, and they can range in value from -1 to +1. In this data set, I have observations that are pulled from three different states of y, a, b, and c. Now, hypothetically, let's imagine this case that I have a new observation, represented by this black triangle here. The question is, who does this observation belong to? Does this triangle belong to group A, group B, or group C? So what you would want to do is calculate the distance between this observation and all other observations. So for example, we'll calculate the distance between this observation in the black triangle and this observation in the orange circle, which belongs to group B. Another near neighbor is this observation in group A and this other observation in group A. So what we do is we calculate the distances, often using a Euclidean distance, which is just the difference in their values squared, and then you square root the sum of those distances. So if I have two x variables, x1 and x2, p in this equation would be 2. So I would just sum the squared differences along x1 and x2 for every pair of points, and that would give me the distance between points I and point j. Now, the critical factor in a kNN algorithm is k. K is the number of nearest neighbors who you ask in order to do the classification. So for example, what I'm showing here in the plot on the left is a case where I've asked the three nearest neighbors who they represent, what group they are sampled from. In this case, my query vector has two samples from A in red and one sample from B in orange. What k nearest neighbors does is ask, who do I see the most? What group do I see the most in this set? In this case, A. So your decision, which is to categorize by popular vote, is to determine that this new observation in the black triangle likely belongs to group A. Now, k is a free variable. You can choose k, and choosing k has important implications on how your classification works. So for example, we can expand it out now to 5 nearest neighbors. So we calculate the distances between this observation and the 5 closest neighbors that all fall in this dashed circle here. That set gives me a set like this: 2 observations in A and 3 observations in B. And since we go by majority vote in the kNN algorithm, we would say that this new observation belongs in group B. That's it. That is the fundamental structure of the k nearest neighbors algorithm. And let me just lay it out as a stepwise recipe here. Step 1, choose k. How many nearest neighbors are you going to ask for a vote? Step 2, for every target observation xi, calculate all dij, which means that for every potential value of x that you want to categorize, take that value and calculate its distance to all observations you have in your training set. Now this is important. You have a data set of observations you're trying to work with. You can actually calculate for any value of x the distance between that observation, either a real observed value or a hypothetical value that you just want to query, and all the pairwise distances to all the observations you have in your data set. You then sort all of those distances, dij, and select the k smallest, which are the closest to xi. And then you categorize based on the median class in step 3, which means that the group that most often occurs in your sample vector of distances is the group that this observation most likely belongs to. Now we can see how kNN differs quite a bit from other classifiers that we have gone over in other lectures. So for example, LDA, linear discriminant analysis, is a very popular classifier that also assumes underlying distributions. Well, I guess kNN doesn't assume underlying distributions, but it also assumes that your data is sampled from some sorts of distributions. In this case here, I have a 2-category classifier, so I have x1 and x2, and I have y being either state A or state B. And what LDA really learns is it takes the distribution estimate for A and the distribution estimate for B, finds the Bayesian discriminant boundary represented by this line, and now any new observations that occur on one of either side of this line get categorized as A or B. And of course, observations that fall perfectly on the line, you can't categorize. That's perfectly under decision boundary. There still is this underlying assumption about the nature of the distributions that generated your data. Remember, LDA assumes that there are Gaussian distributions that generated your observations for A and observations for B. And the difference between LDA, linear discriminant analysis, and QDA, quadratic discriminant analysis, is really just your assumption on the variances of those underlying generative distributions. kNN, on the other hand, just goes off of the distances. So it doesn't assume a shape of the underlying distributions. Now, that doesn't mean it doesn't assume that the distributions are there. It just makes no assumptions about their shapes. So with kNN, you can classify more complicated patterns in your data, like this. So what you see here on the right is, again, a simple binary classification, y is either state A or state B, along 2 dimensions of x, x1 and x2. But now there are basically there's an island or a thoroughfare of observations from group B that sit between observations for group A. LDA and QDA and logistic regression all fail in these kinds of contexts. Whereas kNN can find these complex decision boundaries in complex data. You can have islands of observations, little clusters of observations of one category that exist in a sea of observations for the other categories. Because you're not assuming anything, you're just defining distances. So the arbitrary shape of your decision boundary in kNN really gives you a lot of power and flexibility in performing classification on very complex data sets. But what that means is that your classification is brute force. With LDA, you learn parameter estimates and you distill the problem of finding that discrimination boundary down to a set of parameters of a assumed distribution, a set of essentially linear weights that you have to plug into your data. To find these discrimination boundaries in kNN, you have to use a brute search. So what you try to do is you try to define territories of your space in X that define your categories of Y. Let's stick with this binary classification again of Y being in state A or state B. And you have 2 dimensions of X, x1 and x2. And you see there's this complex shape here. It's clear that there are distinct clusters along x1 and x2 for A and B, but it's not a strictly linear separation. So what you need to do is identify the territories or the space in x1 and x2 that defines Y being in state A or state B. To search for these territories, you have to iteratively go through all possible values of X, so from the minimum to the maximum, and set a precision in between, and use kNN to classify any possible state of X. So you keep sampling, you choose x1 at its minimum and x2 at its minimum, even though you don't have an observation for that particular pair of values. You run kNN, you make a classification estimate, and you define that point in X space as being that value of Y. Let's say A. Then you increase your values by a unit that's determined by your precision, and you do it again. So you iteratively go through all possible values of X that you could observe and define these territories. So you get a space map that looks like this, where the colored boundaries in the back, the orange and the blue colored territories, are defined by an iterative search, where you just set X to a particular state, run kNN, and say this particular value, if you observe anything in that space, will be Y of state A or B. In this case here, your decision boundaries are defined as those points in X space where the vote is an exact tie, or where the vote would hypothetically be an exact tie. So these are cases where unique pairs of x1 and x2 don't allow for you to have a majority vote. You have equal votes in each category. That's how you define your decision boundaries in kNN, through brute force. Now what this does is it allows for you to now take any observation in the future of any pairs of X that fall in this range and automatically classify them. So you can do a holdout test evaluation. You could take your training set here, learn your space of X1 and X2 that define states A and B, and now take brand new observations of X1 and X2 and predict. And so that allows for us to determine the bias-variance tradeoff in kNN. The bias-variance tradeoff in kNN is strictly defined by k. Higher values of k mean higher bias and less variance. So if we set k equal to 1, which is what's shown here on the left, you have the most flexibility of your model. Basically, you're just saying, whoever I'm closest to, that's the group I most likely belong to. This is the most flexible model, which means that its generalizability is fairly low. It can be very sensitive to finding islands or of group clusters, like you see here in this example on the left, where there's this little island of blue and a sea of orange. But its generalizability is pretty impaired. It makes it more and more difficult for you to generalize these territories to new observations of x1 and x2. In contrast, if we increase, let's say, k to 25, which would lead to discrimination boundaries that kind of look like this, which are smoother and more consistent, you can get clear segmentations of broad categories, which increases your generalizability of your model. But it also has a higher error rate. So for example, that little island of blue in that sea of orange, where you have a few observations where y is A, and a set of x1 and x2 where it would otherwise be B, you're more likely to miss those. You're going to just incorrectly categorize those. So this is a good illustration of how your precision of managing your bias-variance trade-off largely is just determined by k, in the same way that in polynomial regression models is determined by p. Now remember, we often evaluate the bias-variance trade-off by looking at performance of the model in a holdout test set and compare the performance of that model, in this case classification accuracy, against what you see when you evaluate it on the training set. And the same idea works with kNN. So if we have a full data set that you're trying to run a classification question on, so let's say y is just a binary state and you have several x's, in order to test the generalizability of your kNN classifier at a particular k, what you would do is you would set aside a set of observations, say m observations here, that will be your test set, so you don't touch those. You take the rest of the data set, m plus 1 through n, and use those as your training set. Now, rather than learn parameters on, let's say, a regression model or an LDA weight to classify the test y's from some model trained on your training set, in kNN, your prediction is by taking every test observation in X. So let's say yi in the test set. Take that row, do kNN based off of the training set. So we'll take one row in the test set, calculate its distance from all the observations in the training set, and use kNN that way to make a prediction for that test observation. And then you do it again for all observations in your test set. So you're not learning any parameters that are being passed back and forth. Essentially what you're doing is you're just taking an observation from your test set, throwing it against all observations in your training set, calculating distances and taking a vote, and then doing it again for all observations in your test set. But at least this gives you a way for evaluating test set accuracy. Now you could do the same thing within your training set. So you could take every observation in your training set, hold it aside, calculate the distances, do kNN classification, and then answer your question. That would give you your training error with which to compare against your test error. So let's take a look at the bias-variance trade-off in a way that we've looked at with other models. Here I am plotting the model flexibility as 1 over k, so that the model gets more flexible as you go from left to right on the x-axis. Because remember, smaller values of k lead to more flexible models. This just makes this plot intuitively aligned with other ways we've shown this bias-variance trade-off. Now if we look at the mean classification error, which is the inverse of accuracy, we see that as you decrease k, or increase 1 over k, your training set error will go down. And that's because you're picking up on the nuanced variability of just that training data set alone. And just like with other types of models, if you compare your accuracy of your test set, data that is not included in your training set, you'll find that there's a point at which your test error increases. So there's a point at which k becomes too sensitive to the unique variance of your training set and starts to reduce its generalizability. So the inverted U-shape, or that U-shape function that you see in the test set, defines that point at which you begin overfitting your data. So the goal is to find the right k that manages this bias-variance trade-off. Otherwise, from a functional point of view in terms of applications, kNN works just like LDA in terms of you just give it a set of x's, you give it a set of y's, and you get a set of predictions. But behind the scenes, there's a huge nuanced difference between things like LDA and logistic regression and kNN. And that critical difference is in how the algorithm is applied and what the decision boundaries mean. And I think kNN as a classifier is quite beautiful because it allows for finding these very nuanced patterns in your data set that don't follow standard distributional assumption patterns that you get with LDA or QDA. So it allows for you to find really wonky relationships in your data with really no assumptions except for nearest neighbors should be of the same group. That's it. That's a single assumption of kNN. Now we've talked about kNN so far in the context of classification because that makes intuitive sense. Now what's interesting is that kNN can actually be used as a regression method as well. And the funny thing about it is that all you need for changing kNN from a classification tool to a regression tool is to really just expand your set of what you think y could be. There's no real difference in the algorithm itself. It's just in your assumptions of the states of y. Now, what do I mean by that? Remember in the classification problem, y is just of a small set of states. So what you're trying to define is make a prediction for every observation yi. You're trying to take your set of x's, try to learn some function that relates a state of x to a state of y. And in this case, you're using some identity function. So you're trying to classify whether or not y is in group k, yes or no. So this I here indicates an identity function which just says that, you're either going to say y is in state k or not. And LDA, it wouldn't be binary, it'd be a group category of any value greater than 2. 2 or greater. But that's it. That's all the classification problem is. Now, you can think about the regression problem in a very kind of similar way, right? So you're trying to predict some state of y, or some observation yi, given some state of x. And in this case now, what you're going to be doing is you're going to assume that every unique observation of y, which remember in the regression context is a continuous distribution, is its own group. So every unique value of y that you have is essentially a group. So rather than having 2 groups, 3 groups, 4 groups, 5 groups, you have n many groups. That's the beauty of regression, really, with kNN, is you're applying it as a classification problem where every value of y is its own unique category. I think it helps to understand this in the context of an example. So let's say that I have an experiment where, again, I'm manipulating, let's say, exposure time to some stimulus, and I'm measuring some skin conductance response. So I'm measuring some stressor arousal response as a result of being exposed to a stimulus of a particular duration. So every observation here can be a trial from the same subject, just plotting the evoked GSR response. And the question would be, does exposure time influence your skin conductance response? Now, for this regression problem, you could apply a polynomial, you could apply, standard linear regression model. But let's look at how we would do it with kNN. So what we would do is we would take every observation I and try to see how similar it is to every observation k. And we would ask how similar each of the near neighbors are in terms of their value of y. And the critical factor here is that every value of y for each observation I, j, and k are considered a unique classification state. So let's just set kNN to 1 for a minute. You would get a regression line that looks like this, where as you change your value of x, remember, you could just try this with any hypothetical value of x. It doesn't have to be a particular observation in your data set itself. So let's just change x and ask, okay, what happens if x is 4, 4.1, 4.2, 4.3, 4.4, and keep increasing. And we just ask, what's the nearest neighbor? So with kNN, with k equals 1, you'll just have these stepwise functions here, where as soon as you get close to one point, you'll say its y is the same state as that observed point I have near me. And you get this kind of stepwise function here, where y keeps jumping state depending on who the nearest point is along that continuum of x. You can clearly see this is the case where I have a highly variable model. So I'm very sensitive to the unique noise in the training set that I'm using. But I'm capturing these kind of nuanced patterns in my data. Now, if I want to increase the generalizability a little bit, I could do something like this. So this is the case where k equals 25. So I have basically a smoothed out function here. And actually, a lot of times you have to trim off some edges here of your you're going to have to window your data based off of the mins and the maxes of x. But you would get essentially a regression line that looks like this. And the line can be completely wonky. The relationship has no assumptions of the distribution of y like you get with both logistic regression and linear regression. So it can be a very powerful tool when you have these very odd relationships between your x and your y. Now, capturing these non-monotonic shapes is really powerful. It can make kNN a very powerful prediction tool. It has no assumptions about the underlying data, but it also makes it a little bit difficult to interpret. You can make a good prediction of exposure time to GSR response in this case, but you don't really gain an intuitive hypothetical understanding of the relationship itself. You don't have some easy to describe parameter or curve per se that kind of compresses that relationship. There's actually really no compression that happens here. It's just a brute force prediction. So kNN in the regression context is really particularly powerful for prediction, but it really doesn't have that much power for inferences. Now, one fundamentally big limitation that kNN has is it is highly sensitive to your model dimensionality. In fact, there's a point at which it just fundamentally fails. Whereas you can deal with dimensionality in linear regression models, and we'll go over those in other lectures. kNN has this fundamental constraint. Now remember, the dimensionality of your model is the ratio of the number of variables you have in X, P, and the number of observations you have, N. With low dimensionality, let's say where I have one variable and 30 observations, you'll get reasonable test error curves that look like this. You can easily see where you manage the bias-variance trade-off. However, with very high dimensionality, let's say the case where you have 30 observations and 20 variables, you get test error that just seems to exponentially increase. In fact, as n approaches p, there just aren't enough neighbors to query, and that distance becomes too sparse. So you just get this failing test error. You never really find a good point at which that you manage the variance bias trade-off or fit your model. And the logic of this makes sense, right? Let's say that I have two dimensions, x1 and x2, but I only have a single observation. Well, in that case, here, p is greater than n. I have nothing to classify. There's no, the entire space is group B or whatever observation that is. Even when n equals p, now let's add this new observation here. This happens to be group A. So I have two observations and two dimensions. That doesn't really give me a clean space to parse. I might get, let's say with a particular value of k, I might get something like this. In fact, with all values of k, I get something like this because I can't go beyond k1 in this case. I only have one other observation I can use to calculate distances against at any point in time. So you start to lose any real precision at describing the problem. In fact, kNN just fails when this ratio gets too high. So kNN is great in many, many ways. It's a very powerful tool for asking prediction questions. It's simple, it's non-parametric. You can use it for both classification and regression questions in the context of prediction. It has no assumptions about your data, so you can detect very odd, non-typical patterns in your data quite nicely and quite easily. So you should think of it as a very powerful prediction tool, so long as you have a low-dimensional statistical question and don't care about inferences.